Hello, my name is Joe LaDuca and I work alongside Julia Romer and Dr. Katie Hark at the Lawrence Livermore National Laboratory on the design, fabrication, and testing of X-ray test objects and a dynamic impactor for traumatic brain injury studies. Dr. Lee Goldstein of Boston University has been working in collaboration with Lawrence Livermore on distinguishing the relationships between concussions, CTE, and traumatic brain injury. Our project is concentrated on studying the physical mechanisms of traumatic brain injury formation within the brain using X-ray imaging systems. This is where LL&L and Army Research Laboratory come into play. Pictured here is the multi-energy flash X-ray system at the Army Research Laboratory. This system utilizes 15 X-ray sources and detector pairs to three-dimensionally capture dynamic events with X-ray imaging. It takes 2D perspectives from multiple angles and three-dimensionally reconstructs them. The non-destructive evaluation group at LL&L has invested in a similar system coming in 2021. By being able to see the physical deformation of the brain in situ, Dr. Goldstein can begin to determine the mechanism of TBI injury and how it can lead to neurodegenerative disease of CTE.
Our project has two main objectives. The first is to design and build a brain X-ray test object that is polymer-based and has a contrast reagent inside that is visible to X-ray imaging systems. The second objective is to design and build a dynamic impactor that uses a basic form of energy deposition, is synchronized with the X-ray cineradiography system, and is a similar size scale to the X-ray test objects. Our desired project outcome is to create a representative brain X-ray test object and dynamic impactor system that can be analyzed utilizing X-ray imaging techniques. The first iteration test object was made of ballistic gelatin with glass capillaries of multiple diameters suspended in the gel. The capillaries were filled with a gadolinium contrast agent, which can be used in future testing with mouse models because it is non-toxic and water-soluble. This object was tested statically, and we analyzed the gadolinium concentration attenuation and spatial resolution of the X-ray images. The imaging was completed using this X-ray cineradiography system. The image on the left was produced by the X-ray system, and the images on the right are the analysis of the image intensity histograms. The spatial resolution was analyzed by measuring the capillary and gadolinium diameters, confirming the X-ray images could accurately image the glass capillary diameters and show the subtle differences in diameters. With this information, we know that the spatial resolution is sufficient for the brain size scale imaging. The second iteration test object was made of ballistic gelatin with an injected gadolinium array pattern to allow for dynamic testing. We will be analyzing the gadolinium attenuation, spatial resolution, temporal resolution, and the gelatin viscoelastic properties.
There are a few primary objectives we were seeking to accomplish with the design of the first dynamic impactor. The amount of kinetic energy delivered to our test object needed to be an order of magnitude such that the motion of the gadolinium drops occurred. This is essential to the radiography image capture as we are looking for this motion. It cannot be a one-shot deal, however. The method must be repeatable so that multiple and future trials can be completed. In order to track energy deposition, the magnitude of energy needs to be quantified and adjustable. This will serve as one of our variables. To ensure we capture the image of the impact, it needs to be synchronized with the cineradiography system. Limitations include remote operation from another room while the system is capturing, and the energy must be contained to a 10 milliliter beaker of the second test object for analysis and safety purposes. The first dynamic impactor for this project is comprised of a 12-inch internally threaded connecting rod, a 12-volt electromagnet, a 12-volt power supply, socket head screw, threaded rod end bolt, and a stand. For the impacting object, we ordered low-carbon steel balls. When the current is applied to the electromagnet, aka solenoid, the steel balls adhere to the bottom, attracted by the magnetic field. Once the current is cut, the magnetic field is removed and the ball falls down. The height of the solenoid is adjustable by moving the connecting rod up or down the stand, and changing the height changes the magnitude of energy deposition. This design overcomes the limitations of the cineradiography system and satisfies the requirements. We can operate the device remotely by syncing the power supply and electromagnet to the cineradiography system. The impactor is wired into the same circuit and initiates capture in the cineradiography system, allowing us to remotely operate the device. Unfortunately, the images of the impactor and ball drop experiments are going through a security clearance process at the lab and have yet to be released for public viewing. Moving forward, we are looking to apply for project funding through Lawrence Livermore or NIH. Additionally, in collaboration with the biomedical department at LLNL, we will be creating more sophisticated brain models utilizing their advanced 3D printing technology. Once the 15-source flash X-ray system is constructed, test objects and impactors will be tailored to fit within the constraints of the system. Direct kinetic energy transfer is one form of energy deposition that may occur in the brain, but future iterations of the impactor may explore methods such as microwave radiation or blast wave propagation, allowing us to obtain a more comprehensive understanding of the mechanisms behind TBI formation. Thank you.